Welcome to the fifth part on our series about threading, parallelizing simple tasks, and eventually we're going to talk about asynchronous development. If you have not seen the other 4 parts, you might go back and look at them, but we are actually doing something a bit special with this part where we're going to do a recap and review the previous 4 parts. So it is possible to just start here if someone directed you here. That's fine. If you want more details, go back and watch the first 4 parts. Now, those first 4 parts were rather technical, and we've been going for a while. So if you're like me, you've completely forgotten what it was we were trying to do in the first place. So today I have a special treat. With my poor artistic abilities, I have created a comic to review what we've done so far. So let's go ahead and take a look. We have a task that we're trying to parallelize, and here is our initial single-threaded approach. We have to go through and read a whole bunch of different files. So we've got our 2 actors here. The left there is our main thread of our application, the only thread we have. And the right is the kernel, the hard drive, whom we're going to be asking for files. The right is a robot. It's not really part of our application. It's not part of userland, so it doesn't get to be a real person. So we arrive, we ask for block 17, and the OS goes off to grab block 17, and we just sleep. Block 17 arrives, and we start to calculate it. While we're calculating our information, the OS is idle. No one is asking it for any kind of disks. Since the OS is our bottleneck in this scenario, and we can have multiple threads, we want to avoid this situation on the right where the robot is sleeping for long periods of time. So this implementation is not ideal, and let's go ahead and add a second thread, and we'll look at our 2-thread solution. Alright, in our 2-thread solution, we now have 2 threads. One is a cool little thread with a headband, and we've got our original main thread. It asks for block 17, and as soon as it gets block 17, it passes it over to our friend and immediately asks for block 18. This way, the robot is kept busy. At no point is he really sleeping or idling because the thread on the left is doing all the calculation. And so we were able to get our maximum time here, and everything was working great, except there's another scenario we might run into. The robot might have all of the blocks we need prefetched in cache and in the memory. So let's look at what happens there. In this case, we'd already grabbed those blocks or files in some previous iteration. That's pretty common when you're processing the same data over and over again. And so it was all fresh in memory. It was in the disk cache for our hard disk. So now we ask for block 17, and we're given it pretty quickly. We go to the computation. Then we ask for block 18, and it's tossed over right away. And so we go to give it to the computation. But now the person doing the computation is still churning away on block 17. So everyone ends up going to sleep, and we're once again in that situation we wanted to avoid. The disk is sitting there idle, but we've got other threads that, other cores that could be doing work. So this 2-thread solution is not very robust. As our workload changes, we aren't able to really flex and adapt. And even if your workload wasn't purely just reading files off the disk, you can have a lot of situations where the workload speed can speed up or slow down based on the parameters of the workload, based on many different variables. And so you typically want something that's more flexible, and you want to have all of your cores in play. So I'm pretending in this fantasy example that I have 4 physical cores. So I can do better than this. All right, now we're talking. We have 4 compute threads. So, since we've got the 4 compute threads, let's go ahead and we don't even need that middleman anymore. We're just going to have our thread pool, and we're going to throw them at the OS there. So they ask for block 17. The robot runs off to get block 17, and he says, I'm ready to get 18. And what I mean there is these hard disks are optimized for continuous reads. They want to read a block, the next block, the next block, the next block, the next block. They'll run a lot faster that way. But that's not what happens. One of our threads goes and starts chunking on block 17, and the next thread immediately asks for block 53. And so that makes the robot a little bit grumpy. So this is kind of an aside. It's not going to be essential to our discussion on asynchronous programming, but it's a problem we had to solve to make sure that we get our maximum performance like we were getting in the 2-thread case. So let's jump back there. All right, so now we've solved that problem by reintroducing our middleman, and his job is to make sure that we're asking for contiguous chunks of blocks. So now we have our 4 thread pool threads, and instead of asking for just block 17, they ask for the whole range of blocks they're going to need. It says, I'm going to need blocks 17 through 22. And our middleman will start fetching all of those blocks. So he says, okay, get me 17. And then when 17 arrives later, he's going to say, get me 18. And then when 18 arrives later, he's going to say, get me 19. And he's just going to stack them all up, and we will start processing those blocks. You may think this is not ideal because we've got those sleeping threads on the left there, but the disk is never going to be idle. It's only really briefly idle while we're trying to figure out what the next range of blocks to grab is, but it's no time at all. So this works really well, and we actually are able to get our maximum performance. The performance we were able to get in the ideal 2-threaded scenario, and if all of the blocks were locally cached, we were able to get maximum performance where we have all 4 of our threads churning away. However, there is another problem. Now let's say whoever's dispatching out these jobs, our web request or something like that, comes in and says, hey, I need some help. All 4 of our CPU threads are busy. Let's look at that problem in a bit more detail. Okay, so we have our job queue here. Jobs are coming in for our thread pool. We have our 4 thread pool workers, and they've all pulled a job off this queue. Read and process file 1, 2, 3, and 4 are all currently active, and they're all waiting on I/O at this particular moment in time. Even our fetcher is just waiting for the disk to actually go get a file. Meanwhile, our easy task has come in. This easy task is easy because it doesn't actually require any I/O. It's a very simple task that we could go ahead and fulfill with our CPU. However, it's not going to get done. In fact, it's going to wait a long time. It has to wait for all read and process file jobs from 5 through 20 to run before it even gets a chance to run. This is not ideal because we have physical cores that could be doing computation. We have a task that needs one of those physical cores to run, and those physical cores are sitting completely idle. This is a total waste and something we need to avoid. And this is the problem where we're going to start looking at how async programming becomes our solution. Now, it isn't the only solution, so let's think about some other ways we could solve this problem. We could prioritize our job queue. We could say, hey, if it's an easy task, then jump straight to the front of the line. Maybe you have to sit idle for a little while for one of those read and process jobs to finish up, and you have a little bit of waste. But for the most part, it works pretty well, except it is really difficult to be able to identify which tasks are easy and which tasks are hard. And it's incredibly tedious for the person writing all of these tasks to be responsible for identifying that fact. We want to put as much of the complexity in our generic thread pool and have it so that the people writing the tasks don't have to really worry about this problem. So we could prioritize this job queue. It's not going to help us a lot for this particular problem. And it's not a terribly popular solution for this sort of conundrum. However, there is another thing we can do, and this has been probably the most popular solution to date. Asynchronous programming is rising in popularity, but normally the sort of classic approach that you would do if you're not going to do asynchronous is you would make a bigger thread pool. So now we've taken our thread pool and we say, okay, I know I have 4 cores, but I'm going to put a bunch of threads in my thread pool. Or maybe I'll make it so my thread pool can grow if there's work to be done. and there's no threads that are working on it. And so here I have a thread pool that has 30 different threads in it. And so what happens? Well, 20 of those threads grab a read and process file job off, and they're all blocked waiting on this I/O. However, when that easy task comes in, we've got our 21st thread that can pull it off and start working on it. We have 4 cores, so since the other 20 threads are all sleeping, that one person can be active and running. And this solution can work. So I don't mean to say that it's not doable. There are a few challenges that you face with this solution. It requires tuning. You don't want to have too many threads because there's going to be a performance hit for having too many threads, and not just the cost of creating all of those threads. That can be amortized away. That's not such a big deal. You only have to pay it once. But it's really the cost of managing a whole bunch of threads. For example, if you have a single job queue and a job comes in, well, you need a thread that can work on that. So you wake up the block, send a notify on the job queue. And if you send a notify all, you end up waking up 9 different threads, and all 9 of those threads wake up. One of them grabs the job, and then the other 8 threads wake up, look at the job queue, see it's now empty, go back to sleep. If you have 100 threads in your thread pool, if you have a lot of just sort of idle threads, then eventually it's going to start putting a drag on your performance. You can code around this. You can fine tune pretty precisely so that you're keeping your thread pool at the right size, but it feels like it's not the best solution. And there is another challenge that you run into when you have this many threads, is you end up with excess concurrency. And it's not just that you are more likely to hit a race condition because you have more threads, more things that are potentially running in parallel, more streams that you have to kind of consider running at the same time. You actually have places you have to lock when you have this many threads and you're handling things in this way that you wouldn't have to lock with other solutions. And we're going to hopefully be able to explore that in a bit more detail, because it turns out the whole point of asynchronous programming is to allow us to not have to grow our thread pool to this giant size, but still be able to avoid the problem we had before where work wasn't getting done because we have a bunch of threads that are blocked on some kind of task. So in the next set of videos, we're going to look at our asynchronous programming methods, see how they work, and we'll see if they deliver on that promise. Do they allow us to use a small thread pool and avoid wasted time? Do we actually have less concurrency than we would have with a giant thread pool? Do we actually get better performance than we would with a giant thread pool? Let's take a look at some of those questions and see what happens. So I hope you're interested enough to keep watching, and I will get the videos ready as soon as I can.